Okay, welcome to chapter 2 of Bio 151. This chapter is called The Chemical Context of Life. There's a lot of chemistry in this chapter, and I need you to just hang with me and do your best to understand this. I know this is not a chemistry class, but I hope that you will see as we go through this chapter and the rest of the chapters in Bio 151 why this chapter is important to biology. So we have to know a little bit about chemistry and a little bit about the way the molecules bind and interact in order to understand biology. So hopefully we can get through this chapter together. So we need to start with atoms. So this is the periodic table. This looks familiar to a lot of you probably. You've seen this before. And we need to talk about the difference between an atom and an element. So I think this may be a little mixed up for you. Not sure why. But we have here an element. So this is the definition of an element. An element is matter that can't be broken down by ordinary means. So an element is made up of one type of atom. So if we might have an atom of carbon. So carbon is an element. We might have an atom of helium. So helium is an element. We might have an atom of magnesium. Magnesium is an element. None of these things can be broken down by ordinary means. Now, an atom is the smallest unit or the amount of an element. An atom is sort of like a measuring stick, like a gram or a liter. We can have atoms. It's the smallest unit or the amount of an element. So the smallest unit of carbon that we can have is an atom. So we have atoms that make up or that are used to measure elements, and elements are found on the periodic table. Okay, so we need to talk about what are atoms made of. So atoms are made of subatomic particles, and there are three that we are going to talk about. We are going to focus on the electron, the proton, and the neutron. So the electrons, as you can see, orbit out here outside the nucleus. So this thing circled in green here in the center of the atom, that is the nucleus, but the electrons you can see are out here orbiting outside the nucleus. Electrons are negatively charged, and they are much, much, much smaller than protons or neutrons. When we talk about protons and neutrons are both present in the nucleus. So we have protons and neutrons in the nucleus. Protons are going to be positively charged, and they're about the same size as neutrons. Neutrons we're going to see also in the nucleus. And neutrons have no charge and are about the same size as protons. So within the nucleus, we have our protons and our neutrons. Electrons orbit out here around the nucleus. So we need to understand this atomic structure in terms of the periodic table. So on the periodic table, you have something called the atomic number. So the atomic number tells us the number of protons in a nucleus. So for example, the atomic number of hydrogen is 1. That tells us we have 1 proton. The atomic number of carbon is 6. That tells us we have 6 protons. This is key. If there's no net charge on an atom, and we will talk about atoms that have net charge in a moment, but for right now, we are talking about atoms that have no net charge. The number of protons is equal to the number of electrons. So that's going to be key for us for now. So no net charge, the number of protons is equal to the number of electrons. Remember, those protons are positively charged. Those electrons are negatively charged, so they would balance each other out. That is not always going to be the case, but if we are talking about atoms with no net charge, that is the case. Now, when we talk about the other term that we need to be familiar with is mass number. So mass number tells us, obviously, the mass of the atom. So when we talk about mass number, we talk about the total number of protons plus neutrons. So for carbon, for example, it has a mass number of 12. That means it has 6 protons and 6 neutrons. We can figure out the neutrons always by doing the mass number minus the atomic number, which remember is the number of protons. That is equal to the number of neutrons. Okay? So that's how we know the number of neutrons. Mass number minus atomic number, which is the number of protons, is always equal to the number of neutrons. Now, atoms are not always going to have the same number of neutrons. So neutron number can vary. Now, proton number can never vary. If we have a carbon atom, it's always going to have 6 protons. But we might have a carbon atom with something other than 6 neutrons. So most elements are actually a mixture of atoms with different numbers of neutrons and therefore different masses. So the definition of an isotope, the definition then of an isotope is atoms of the same element having the same number of protons and electrons but with different numbers of neutrons. So the mass is always sort of an average of these isotopes. So we always know, let's take carbon for example. Carbon, always has 6 protons. But it can have 6 neutrons. We can have carbon atoms with 7 neutrons. We can even have carbon atoms with 8 neutrons. So all of these would have different masses, different atomic masses. This atom with 6 protons and 6 neutrons would have an atomic mass of 12. The atom with 6 protons and 7 neutrons would have an atomic mass of 13. And the atom with 6 protons and 8 neutrons would have an atomic mass of 14. So that's where we get our average atomic mass. So here we are on the periodic table. We can find a couple of these key numbers on the periodic table. So if we look at this, for example, this top number, that number 11, that's our atomic number. The bottom number below the name or the symbol of the element, that's always going to be your mass number. So you will need to know how to read the periodic table for your exam and understand what these numbers mean. Also, we need to understand that the way the periodic table is arranged. So we have horizontal rows and vertical rows, and we group those elements based on similar properties. That's about all I want you to understand for that. Okay, so why do we care about atoms and elements? Well, that's because it gets us to molecules, compounds, and mixtures. If you remember back from chapter 1, we started out with atoms on our organizational chart, and that got us up to molecules. In biology, we are very interested in molecules. So that is 2 or more atoms of the same or different elements joined together in a chemical bond. So we can have 2 atoms of hydrogen, 2 atoms of nitrogen, or we can have things like NaCl. So they can be the same element, they can be different elements. That's called a molecule. A compound is when we have it's composed of 2 or more different elements. So that is very key. For a compound, the elements have to be different. So that H2, that N2, that O2, those are not compounds. Those are molecules, but they are not compounds. A mixture is when we talk about 2 or more elements intermingling in ways that are not bound. So we think about things like a tossed salad. We have lettuce, cucumber, salad, cheese, but those things are not bound together. They're not stuck together, but they're all in that mixture. So when we think about how things bond, we have to think about what are called valence electrons. These are those electrons that, again, orbit that nucleus. Remember, we said that's where electrons are. The valence electrons are the ones that are going to be in the outermost shell. These are the ones that are going to be involved with bonding. Okay, and you're going to learn more about this in chemistry, but for right now, this is what I want you to know about this. The chemical behavior is mostly determined by these valence electrons, and how we know whether or not an atom is going to bind is determined by these valence electrons. Atoms always want 8 electrons in their outermost shell. That's key. That's called the octet rule. So octet rule, and that's going to be key for us for understanding bonding. So if an atom already has 8 electrons in its outermost shell, we say that it is chemically inert, meaning it does not react or does not bond. So let's think about the different types of bonds that we can have. We're going to introduce them and then I'll go through them. So we can have ionic bonds, covalent bonds, or hydrogen bonds. Ionic bonds are going to be bonds between ions. And we'll talk about what an ion is in a minute. Covalent bonds, so in an ionic bond, electrons are either going to be gained or lost. So electrons gained or lost in an ionic bond. Covalent bond is when we're going to have electrons are being shared between two elements or two atoms. And then a hydrogen bond is a type of covalent bond that we see specifically a lot of in biology. So we'll talk about that as we go through. Let's look at ionic bonds. So before we talk about ionic bonds, we really have to know what is an ion. So we have to define that. An ion is an atom with either fewer or greater electrons than a neutral atom. So let's look at sodium. Here's a neutral atom of sodium. The atomic number of sodium, if we see on the periodic table, is 11. That means it has 11 protons. And because this is a neutral atom of sodium, it also has 11 electrons. So if we count them, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if we look in that outermost shell, we see one little electron here. This is our valent electron. That's the one in the outermost shell. Well, sodium is not happy with that one little electron in its outer shell. Remember, we want 8 in our outer shell. So what sodium actually does is it gives up this electron. It wants it to go away so that it can be happy. So now we have an ion of sodium. Okay, so sodium, in order to form an ion, loses an electron or gives up an electron. So now we have a sodium ion that has a positive 1 charge. That means it has lost an electron. So we now have 11 protons and 10 electrons. So if we count them now, we have 1, 2, 3, 4, 5, 6, 7, 8 in our outermost shell, and then 1, 2 electrons there. So we have a total of 10, but we have 8 in our outer shell, and that makes sodium very happy. It meets the octet rule. Now, not all ions lose electrons. Some ions gain electrons. So here we have a neutral atom of chlorine. The atomic number of chlorine is 17, so we have 17 protons in the nucleus, and we have 17 electrons. So if we count these electrons, let's go ahead and count them again. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And if we count, we can see that chlorine has 7 electrons in that valent shell. So it's almost to that octet, but not quite. It's missing 1 electron. So what chlorine wants to do is actually take on an electron. So it generally finds an atom, maybe like sodium, that wants to give up 1 electron, and chlorine says, that's great, I will take it. So we now have a chlorine ion of a -1 charge. So we still have our 17 protons, remember that doesn't change, but now we have 18 electrons. And if we count those electrons in the outermost shell, we now have 1, 2, 3, 4, 5, 6, 7, 8. So chlorine has met its octet rule and it is happy. When we have molecules like, atoms like sodium and chlorine coming together and sodium giving up an electron and chlorine taking on an electron, we call that an ionic bond. This is what we call sodium chloride or table salt. This is NaCl, so sodium and chlorine, joined in an ionic bond where one atom, sodium, gave up an electron, and one atom or ion, chlorine, took on an electron. This is an ionic bond where atoms are either gained or lost. Alternatively, we have covalent bonds. Covalent bonds are where atoms share electrons. So we can have single covalent electrons where we can have single covalent bonds where one pair of electrons are shared. We can have double covalent bonds where two pairs of electrons are shared, or triple covalent bonds where three pairs of electrons are shared. Now, with covalent bonds, we can also have something called polarity, nonpolar or polar. In nonpolar covalent bonds, electrons are shared equally. Okay, so nonpolar, we have equal sharing of the electrons. The electrons spend as much time, equal time around each of the atoms in the bond. In polar covalent bonds, we get unequal sharing. So one of the atoms is going to be an electron hog. It's not going to share equally, all right? So that's going to be important for us. Okay. Whether or not we end up with nonpolar or polar covalent bonds depends on something called electronegativity. So this is another sort of vocabulary word definition. Vocabulary word for us that we need to define or know the definition of. This is an atom's attraction for the electrons in a covalent bond. So the more electronegative an atom is, the more strongly it pulls those shared electrons toward itself. So you can think of, for example, a toddler. A toddler is typically going to be very electronegative towards a stuffed animal. He's not going to want to share that stuffed animal. He's going to pull on it, he's going to hold it tight, and he's not going to want to share it. That is what atoms that have high electronegativity are like in terms of their electrons. They have a tight pull on those electrons. They don't want to share them. They want to hold on to them, and they don't share them equally with the other elements or the other atom bond. So an example of a covalent bond we see in oxygen. I don't know why this is square. It's just something when it got converted on the iPad, it ended up being square. But we know that it should be round, just like the others, along with the electrons. But here we have an oxygen atom. Oxygen atoms have 6 electrons in their outermost shell, or 6 valent electrons. And we have another oxygen atom, also with 6 electrons in its valence shell. Neither one of these guys are going to give up their 6 electrons or get somebody to give them 2 more electrons to reach that octet rule. The best thing that they can do to be happy to reach that octet is to share. And so that's what we hear in this covalent bond is we end up with 2 pair of electrons being shared between the atoms. So this is a double covalent bond because we are sharing 2 pair of electrons. And now everybody's happy. So each oxygen now has 8 electrons in its valent shell. Now this would be a non-polar bond, which means we have equal sharing. The reason being that these are both oxygen atoms. They're going to exert the same amount of pull on the electrons. So if one of these were a hydrogen atom, we would get a different sharing. Oxygen and hydrogen have different electronegativities, but they're both oxygen, so they both have equal electronegativities, so they're equally pulling on those electrons. So this is a non-polar valent bond. So this got chopped off a little bit, but you can see we have examples of non-polar and polar covalent bonds. I'll tell you one important key to remember is that when you have non-polar covalent bonds, you almost always have them between the same element. So you can see we have 2 oxygens, 2 nitrogens, 2 hydrogens. If there are 2 different elements in a covalent bond, it's almost always going to be polar. All right, so that's important to remember. 2 different elements, almost always going to be a polar covalent bond. All right, so lastly, real quick, I want to talk about hydrogen bonding. Hydrogen bonding is a special type of covalent bond that happens, we see it quite a bit in biological molecules. So we know that water is dependent upon hydrogen bonding. Things like DNA is held together with hydrogen bonding. Proteins rely heavily on hydrogen bonding. So we see this a lot in biology. These are pretty weak interactions, weak bonds. But they occur between an electronegative atom and hydrogen. So hydrogen is obviously always going to be involved in a hydrogen bond. And that other electronegative atom is almost always going to be oxygen, although it can be nitrogen or sulfur, but it's almost always going to be a special covalent bond between hydrogen and usually oxygen. So again, we see these within and between lots of molecules in biology. Now, I said that the hydrogen bonds were weak, and I also said they hold together our DNA, right? That doesn't make a lot of sense that we would want our DNA held together by something strong. But the idea is there's strength in numbers when it comes to hydrogen bonds. So individually, they are weak. But when we have thousands and thousands and thousands of hydrogen bonds all holding one molecule together, it becomes very strong. So if you look at the link between the skydivers here, individually, if we look at one link, that would be weak. But taken together, when we take the whole group of skydivers together, it's a pretty strong bond. Okay, so chemical reactions. Why do we care about atoms, and why do we care about elements, and why do we care about molecules? Because that leads us to chemical reactions. Chemical reactions make and break these bonds. So when we have a chemical reaction, the starting materials are the reactants. The final products, or the final molecules that we make, are called the products. This is the crux of biochemistry right here. So you guys might know that I'm a biochemist. This is my bread and butter. So what I care about is the chemical reactions that take place in the body. And so this is a little introduction to that, a little taste of that in seeing the interface between biology and chemistry. Everything that happens in your body, everything that happens in your cells is dependent upon these chemical reactions being able to take place, us being able to make and break chemical bonds. So we need to know a little something about chemical reactions and what they look like. So we have a really simple chemical reaction here of the production of water. So our reactants over here are hydrogen and oxygen, and then our products are 2 molecules of water. So anytime you see that arrow, that's showing you the direction in which the reaction proceeds. So we take 2 molecules of H2 plus 1 molecule of O2, and we produce 2 molecules of water. It's a very simple chemical reaction, but essential to biology. So we know that chemical reactions usually some chemical reactions go to completion, where all of the reactants are converted to product. That's not usually the case in biology. What we find most of the time in biology is that reactions are reversible, meaning that they can go backwards. So we can take that product B and convert it back to reactant A. So we have forward reactions, or we have backwards reactions. When the forward rate, what we say is when that forward rate equals the backward rate, we have what we call chemical equilibrium, and that is key. It has nothing to do with amounts of products or reactants. It is the rate of the reactions. When the forward reaction rate is equal to the backwards reaction rate, we reach chemical equilibrium. We'll talk a lot more about this in the chapter on water, but for now, that's essential to know. So hopefully this was a brief little introduction to biochemistry for you, and hopefully you can appreciate why chemistry is so important to biology. So I'll see you in class.